All right, guys. So I haven't seen the participants amount change in a couple seconds now, so it looks like we will go ahead and get started. So first of all, thank you everybody for coming. On behalf of myself, Nick, and Cade, we just thank you guys for taking some time out of your Tuesday night. And we hope you guys find the information that we present to be very helpful. All right, so our schedule, right? We have a predetermined set of slides that we go through, a little bit of basically like kind of a recap on your lectures and a little bit of examples tossed in there. That will take about an hour-ish. We're hoping to get it done to about 45 minutes or so. And then I will actually, as soon as I finish talking here, make a poll and we'll send that out to you guys via a link. And you guys can vote on which questions you guys would like to see done by us three, right? So Gauss's law, Coulomb's law, things like that, right? So be on the lookout for that. I'll send an announcement in the chat and you guys can click on that. But for now, I will hand it off to Cade, who will go over uncertainty and Coulomb's law. So Cade, you all ready to go?
I'm getting that all pulled up right here, so we might take a moment to get the poll a little bit farther along.
Oh, good. All right, well, I'm passing it up to you so I can work on that poll. So let me know if you need anything.
Can everyone see this now?
I can see it, Cade. You're good.
Okay. Thanks for the feedback there. Hello, everyone. Welcome to the Block 1 review for electrostatics. Tonight, we're going to be going over some of the points that we have in this presentation that we think are most salient for your first exam coming up on Thursday. And in addition to that, whenever we finish, kind of like what Tyler said, we'll kind of ask some questions, see what you guys want to review more in depth and get feedback from you guys about things that you might still be confused on. And so in order to make the best use of our time, I'll go ahead and get into it. And so to start out, we will be doing a refresher on uncertainty. And so this is going back to block 0. And essentially what we do here is that in order to determine how much a particular variable has how much it affects our outcome of a function, such as what we have here, indicated by f, we can find the uncertainty for each of the variables, those being either x, y, or z, and we can add that uncertainty to our measurement in x and find what that function yields with that uncertainty added to it, evaluate the function without that uncertainty, and from that we can see how much our function is actually changed by each of these measurements. And so this can not only be done for x, it can be done for y and z as well. And then in order to solve for the total amount of uncertainty that is associated with each of these variables, we can do what we see here at the bottom, in which we square each of them for x, y, and z, find the sum of those, and take the square root. And so now kind of getting into something that's a little bit more related to physics too, we can do this with something like electric field. And so in the problem statement here, what we have is that we're trying to find our electric field, and it's over a distance of 72 centimeters. And as you'll see on the next slide, we have some associated uncertainty with that. And along with that, we also have a charge of 4 microcoulombs. And so we'll be just applying this to Coulomb's law that we can see down here. And knowing that we have uncertainty associated with each of these things that we've measured, that being the charge and the distance that it's acting over, we'll simply apply what we showed on the last slide to this expression. And so this is once again stating what we had on the last bit of the presentation, essentially just once again stating what we have measured for both the charge and the distance. And then here also put nicely for us is the uncertainty for each of these indicated by delta Q and delta R. All right. And so it's going to be very similar to what we did for the function that was dependent on x, y, and z. But in this instance, since we have uncertainty with our charge and with our distance, what we will do is essentially calculate our electric field with the uncertainty of Q added to our original measurement. And then from that, subtract our measurement of electric field without that uncertainty to determine how much that actually changes or alters our electric field in the end. And so you can see that that is quantified there in the first portion. And then we did the same thing whenever we're relating it to the distance. And a key thing to note here is that you want to keep in mind that if we're doing this with relation to distance, you would want to do the distance that we measure plus that uncertainty and then square it, as you can see in the bottom portion. And then similarly as to what we did in the first part with Q, we have the quantification of this uncertainty but associated with the distance shown at the bottom. I see a few things showing up in chat. I'm going to check that real quick. Okay, looks like it's from Nick. Okay, and so now in order to solve for the total uncertainty in the electric field, all that we would have to do is square each of the uncertainties that are associated with Q and that associated with the distance R, and then find the square root of that in order to determine the total amount of uncertainty in our electric field from what we had originally measured in our charge and the distance that it was enacting over. And this is a good thing to kind of get a refresher on, because not only will you likely see it on this exam, but as we progress through the course, you'll continuously see it in exams 2, 3, and even in the final. They generally throw in a question that comes back to this just so that you guys aren't forgetting as you progress through the course, okay? So I believe that that is our worked example for uncertainty. Are there any remaining questions or anything that's not entirely clear before we progress? All right. So if we don't have any outstanding questions about uncertainty, we will then move on to Coulomb's law for discrete charge distributions. And so that can be seen modeled here, in which E is representing our electric field. And the equation that we're using here combines Coulomb's constant K, described at the bottom of the screen as 1/4 pi epsilon naught, multiplied times the charge that we're observing, which is in Q, all over the magnitude of that R vector to the third power, multiplied times just the R vector itself. And so moving forward, whenever we're dealing with things like this, and this is very similar to what we did in a graded group activity in Studio, we can apply the principle of superposition. And essentially, what this is telling us is that if we are trying to determine the electric field at some point, let's say P, that we can get the total amount of electric field on that point by summing up the contributions of all these different charges around it. And that will tell us how much is enacting at that point, P. And so simply all you would have to do is sum them as shown in this expression. And I believe in this example that's provided by Nick, this was for in the Y or J hat direction. And so this is kind of going back to what we did in a graded group activity. And this applies to Coulomb's law, and especially whenever we're dealing with discrete charges. All right. And so extending this to a little bit more of a complex, a little bit more involved method is whenever we have continuous charge distributions. And so one of the first things that we introduced in class for this was whenever we had an infinitely thin line that had a charge distribution along the y-axis. And so in order to determine how to deal with this, what we can do is we can express electric field in its differential form as the differential electric field dE. And it's very much analogous to what we do for discrete charges, except for this key difference that we will now be expressing charge as differential charge dq, so that we can find the contribution of this infinitesimally small area of charge and the electric field that it produces. And so as you can see, it's very similar to what we have just kind of introduced. It's k times dq over the magnitude of that r cubed multiplied times that r vector. And another thing to keep in mind whenever we're doing this, as I kind of showed on the last screen, was that whenever we're drawing these r vectors, keep in mind that you want to go from the points from the infinitesimal charge to the observation point. So that's kind of keep in mind that we want to go from source to point in order to define that r vector, okay? All right, there's actually a question in the chat that says something along the lines of, can we clarify when to use r cubed and when to use r squared? So this is a great question. Essentially, and there's a little bit more of a mathematical explanation as we proceed. These two equations are exactly equivalent. And what this is showing here, if I can pull up the annotation, is that this r hat term is essentially going to be the unit vector that is defined as the r vector over the magnitude of that same r vector, right? And so these are exactly equivalent, but in the terms whenever we are trying to find, let's say, the magnitude of the electric field, then because we're just finding magnitude and no directionalities associated with our electric field, we can simplify just the magnitude of electric field down to E is equivalent to KQ over R squared. So I hope that gives a little bit of an introduction as to when to use that r to the third power and when to use r to the second power. But we will touch on that again as we progress on. There's some slides that have it put quite well as we go forward. But essentially, the thing to keep in mind here is, even though the notation can be a little bit odd, these are essentially the exact same. But whenever we are finding the magnitude is whenever we can truly simplify it down to just have r squared. All right. I hope that answers that question for now. And now moving forward. All right. And so this is actually the very next slide that goes into that same idea. And so essentially the main takeaway from that is that Coulomb's law will always have a dependence of 1 over r squared. All right. And yes, for the other question in chat, this is being recorded currently, and we will post it on later on. So once again, this is just restating what I said on the previous slide, that this r hat vector is a unit vector, and it specifies both the direction of the electric field and the magnitude of it. And so in other words, if we're just finding the magnitude of the electric field, this will simplify to 1, in which case you can just use, as we said, KQ over r squared. And so once again, shown quite well by Nick himself. Costin, thank you very much for the slides. We have this shown here, wherever it's saying that both of these forms are exactly equivalent. It's just that the r hat vector is a different representation of the same thing. Okay. So now, since we're dealing with continuous charges, it's good and it's always nice to come back to how we describe these charge distributions. And so essentially, starting from our simplest case of the one-dimensional, how we would describe dq is essentially saying that we have lambda times dl, where lambda is defined by the total amount of charge over the length of that object. And so if we were dealing with something wherever it's like, let's say, an infinitely thin line on the y-axis, we would go the total amount of charge over essentially the height of that object. And we would just continue to expand this idea into different dimensions wherever we have, for 2D objects, sigma times dA, wherever sigma is defined as the total amount of charge over the area of that object. And so that also proceeds for 3D objects, wherever rho is q over the volume. And the thing that I would like to point out, and I think will also be addressed once again on the next slide, is that for the total amount of charge that you see down here, that we can always have it as q is equivalent to the integration of whatever our charge distribution, charge density is, multiplied times the differential of whatever volume, area, or length. And this holds true, this at the bottom holds true for both uniform and non-uniform objects or charge distributions. And that is because essentially, whenever we have something wherever it is uniform, we can still do the equation on the bottom, but we have the nice simplification that we can pull out whatever rho, sigma, or lambda is, um, as opposed to whenever we're dealing with something that is non-uniform and that charge density has a dependence on r, in which case we would want to keep rho on the inside of the integral. And so this is just saying that same idea once again, that q is always equivalent to dq, or the integration of dq. And so this works all the time, but in special circumstances, we can simplify things like pulling rho out for uniform charge distributions. All right, and so now we're going to kind of deal with a more tangible example wherever we have some amount of charge distributed across a sphere. And so the key things to note here are that Q, capital Q, is indicative of the total amount of charge for that object. The capital R here is indicative of the sphere of the radius of the sphere. R will be that for our Gaussian surface, and for this problem, we will be dealing with a Gaussian surface that is actually inside of the physical sphere. So its radius will be less than that of our sphere's radius. All right, so now we are going to try and solve for what the total charge enclosed in our Gaussian surface is. So the first thing that we will want to do is define what rho is, because this is a three-dimensional object. And so to do that, we could take the total amount of charge, Q, from our problem statement, and divide that by the total amount of volume. And so this would be the same process for any other three-dimensional shape, including cylinders or anything else that you might be proposed. And it's always a good thing to keep in mind, commit to memory, what the volume of each of these objects might be, because that will be a reoccurring theme throughout the course. And so simply to define rho, total amount of charge over the total amount of volume. And the next thing, and the thing that I think trips up students more often than defining rho, is finding out what our infinitesimal volume is, or our dV. And so a great way to think about this, and something that Nick put here quite well, is you can think of this as essentially the very thin amounts of surface area that make up the entirety of the volume. And so essentially what this is saying is that whenever we're doing this integration of dV, is essentially associating very, very thin shells of different radii to each of these of different radii that will inevitably make up the entirety of the volume of the sphere. And so this is a very conceptual way to visualize what's going on, because we will be essentially building the volume of this through that integration as we go from 0 to the R of the Gaussian surface. And so what Nick says here is that we can think of this as an onion peel, and it's just made of very thin slices that whenever they're all put together will end up making the volume of the object that we're looking at. And then the other thing that we want to keep in mind is the direction of our differential. In this case, it would be in the R direction for that sphere, And so this is a very conceptual way to think about it, essentially building the volume through successions of our surface areas. But another way that is a little bit easier to grasp is essentially defining what our volume is, in this case, what we have described for the sphere. And then simply we can just take a derivative of it, and that yields us what our surface area is. And this, by just simply moving over what we took the derivative with respect to, also describes what our differential volume is for a sphere. And this will also work for something like a cylinder, in which case the volume of a cylinder would be equivalent to pi r squared times L, essentially giving you a projection of that surface area, or the cap, and then extending it the length L that it goes up. And so you would use the exact same process wherever you would take the derivative of this volume with respect to r to get 2 pi rl, wherever 2 pi r kind of associated with the circumference, and then multiplying that times the length gives you the surface area that you would have associated with this infinitely long cylinder. And then simply you can move the dr over, just like we did in this portion, to get the differential volume associated with a cylinder. And so this is a way that's a little bit less conceptual, but will still yield the same answer, the same result for our differential volume. All right. Nothing in the chat right now. And so kind of putting all these things together, now that we've defined what rho is, what we've defined what the differential volume is, we can put this all into our integration wherever we have the bounds going from 0 to that lowercase r, defining our Gaussian surface. And so this is essentially the mathematical steps that you would want to take. Keep in mind that this r that is associated with our sphere is going to be constant and can be pulled out of the integral. And we simply end up with that Q is equivalent, or Q enclosed is equivalent to the total amount of charge multiplied times the radius associated with our Gaussian surface cubed over the radius associated with our sphere cubed. I'll leave that up for a moment for anyone to look at the math if they have any questions. All right. And so essentially, one of the things that is nice to realize here is that since we were dealing with something that is uniformly charged, we can pull out that rho, as we kind of stated earlier. This is one of the simplifications that we can do whenever we have uniform objects of charge distribution. And this helps us to make the integration and the math overall quite a bit simpler. And the kind of key takeaway here is that we can pull out what our rho is, and then that just leaves us with the integration of dV being equivalent to our volume. And you end up getting the same expression there, just a little bit less complicated on the math side of things. All right. It looks like here we're about to move into another example, it looks like. I'll give it a few moments in case anyone has any questions or anything that they want to kind of recap from what we just went over. All right. Can you recap when to use surface area versus volume equation in Gauss's law? All right, so Gauss's law is actually going to be coming up in what Tyler will be covering, so I'll leave that to him, but I'm sure that he will be able to answer that question as he proceeds through. All right, we have another question. How do we calculate the rate at which the surface is losing charge? I'll probably leave that to the time afterwards because that seems like it's a little bit outside of the realm of what we're covering here. All right, does the derivative of volume for finding dV work for other shapes like a cube? I would have to work through that. I would assume that, Nick, do you have any indication there? I'm assuming that if you're doing...
So like if a cube has side length x and I take the derivative of it, that gives me 3x squared, which is not the surface area. To be honest, I don't know why that is or what's special about spheres and cylinders, but thankfully spheres and cylinders are the only objects that we deal with when using Gauss's law.
It's likely the radial component then, but yeah, for this class, I guess is the kind of asterisk that we should put on there. For any of the objects that we will ask you guys to deal with, that will hold true. All right, and so now moving into the last example that I will walk you guys through is we're going to be dealing with finding the electric field due to a ring of charge. And so this should look a little bit familiar. We've kind of ran through a similar example in class, and essentially we're trying to measure the electric field at some point above a ring that's centered on the XY plane. And so running through everything that we've kind of just described, we would want to define first what our general equation is. So we would want to use Coulomb's law for continuous charges, and then describing what our charge distribution lambda would be. And so we would do that by taking the total amount of charge over the total length. And for that, it would just be the circumference 2 pi times the radius of that ring. And then simply we can put that into our equation for dq, wherever dq is lambda times dl. And leave that up for a little bit so that everyone can look at the math associated with it. And then the next thing would be describing the R vector, and essentially that's pointing from our source to our point. And so what we can do here is take final minus initial to describe this vector. And so we know that we're ending up at a point that is centered on the XY plane. So it has 0 and 0 for X and Y components, but it is elevated to a point ZP. So that associates all these first portions. And then from our initial points associated with the range, we find our cosine theta and our sine of theta for the X and Y components respectively. All right. And so the following mathematical steps are just taking the magnitude of that R vector by simply squaring each of its components, and then simplifying it down to this expression of the square root of R squared plus ZP squared. All right, and then simply we would just want to put everything together into the overall equation for Coulomb's law that we showed previously, in which we have K dq being described here, this being dq, this being the magnitude of our R vector, and then this being our R vector overall. And so I believe that the next portion will show us how to get both the X and the Y components. And so essentially the X and Y components can be taken by just multiplying times that component of our R vector. So if we were trying to find the X direction, we would just want to multiply times the I hat component, and for the Y direction, multiply times the J hat component. All right, I believe that's the end of my portion as we transition into Gauss's law with Tyler.
Can I interject real quick?
Go for it.
Yeah, there's a question in the chat. Why are we doing this in 1D? And can you scroll up to the picture real quick?
Yes. There we go.
Yeah, that's actually a very good question, because you'd think, why would we do this in 1D when the ring of charge sort of occupies space in a plane? So why wouldn't it be 2D? And the reason is because it's a one-dimensional charge distribution, because charge is still distributed along a line. That line might be curved, but because it's distributed just along the line in a circle, if you will, that's why it's 1D charge distribution. Another way to think about it is there's one parameter that describes where we are on that ring of charge. It's theta, because R never changes. I don't know if that answers the question or not. Cool. Yeah, super good question.
All right, thank you. Thank you for directing that back to the chat. And so I believe that that wraps up our example for the ring of charge. Excuse me, there was one more in which we can see the overall simplified equation that also corresponds to finding the electric field of a charged ring that you have on your equation sheets. All right, it looks like there's another question. So if it wasn't a ring of charge and more like a plane, we should do it in 2D. I would say I would agree with that, because you would need both the X and the Y components in order to describe where you are on that object. All right, well, I believe that that's going to transition into Gauss's law, and I can stop sharing so that Tyler can begin.
Awesome. Thanks very much, Kate. You can hear me, right?
Yes.
Cool. All right. Had to join on my iPad, you know, the whole shenanigans that go along with Zoom. All right, so let me share my notes here and we can go from here. All right, so before we transition, does anybody have any last questions about uncertainty or Coulomb's law that we're kind of already touched on briefly, just so we don't get too far away from that topic? Feel free to unmute yourself or ask in the chat so we can get those answered. But if not, then I will go ahead and get started. I don't see anything quite yet. Awesome, cool. Okay, so I will go ahead and get started. First of all, thanks, Kay. That was a very good introduction to uncertainty and Coulomb's law. I very much appreciated that. Quick reminder, I resent out that link to the Google form that I created. Please make sure to vote on the questions you guys would like to see done, right? That's how we gauge which questions to even go over, right? Because we want this to be a good use of your time, not just us sitting here going over things you don't care about, right? So feel free to let us know. But other than that, I will go through my part here. Okay, so Gauss's law, right? This is the big kind of the overarching topic in Unit 1, right? Everybody seems to have some some qualms with Gauss's law. So we'll go through it, right? So first things first, right? We're just going to start with just the general equation of what the hell Gauss's law even is, right? So it's going to be this equation right here, right? So we're going to say that the left-hand side, right, the electric flux through a closed surface, right, or the surface integral of E dot dA is equal to the amount of charge I have in my object divided by epsilon naught, the permittivity of free space, right? So before we do anything else, it's important to note that both of these sides of the equation are equal to electric flux, right? Both of them are, okay? So if you get to questions on your exam review, things like that, where it asks for electric flux, you are free to use either the left or the right-hand side to solve your problem, right? Occasionally you'll be given conflicting information, right? Sometimes you'll just be given, hey, I've got a charge in this like pyramid, for example, right? And in that case, it would make more sense to use the right-hand side, right? So I just wanted to introduce that to you, right? If we're asked for flux, you can use either side, right? That is not inherently a Gauss's law problem. A Gauss's law problem will ask you for the electric field at some radius within or outside of a shape, okay? So just a quick little reminder as to what that actually looks like, right? But yep, so just as a definition, so Gauss's law asserts that the electric flux through a closed surface is proportional to the amount of charge enclosed, right? So like I said, just a definition of what we've been dealing with here, right? Hopefully that equation looks a little bit familiar to you guys at this point, right? So now a little bit more about electric flux here, right? So I already covered that the left-hand side is the most general equation for electric flux, right? We established that both the sides are equal, right? But in its most general form, electric flux is known as the integral of E dot dA, right? And for all of our intents and purposes, right, for Gauss's law problems, we are concerned about the flux through a closed surface, right? So this is things like your spheres, right? Like your cylinders, right? Like all of those shapes, those are the ones we are concerned about, okay? So moving forward a little bit from that, right? If our electric field is uniform, right, along a certain radius, and the area is flat, right? Let's say we had a plane, for example, right? Or some, we can approximate it to be flat. The flux becomes that E dot dA that we love so much, right? Or EA cosine theta, right? We can get rid of that integral, and we'll cover those symmetry arguments a little bit more in detail in a couple more slides. But yep, in its most general form, right? Flux E dot dA, where the dot product is a measure of how parallel two vectors are, right? So if I've got two perpendicular vectors, the dot product of those two would be 0, right? Whereas if I had two parallel vectors, the dot product of those two vectors would be 1, right? Because the angle between them is 0, and the cosine of 0, right, is equal to 1, right? So just a little bit of a mathematical sort of explanation as to where that comes from, right? Why we like to get to E times A. All right. So from here, unless there's any questions about just electric flux in general, right? Nick has a great image, right, of just visualizing what the heck flux even is, right? I guess in layman's terms, I would define flux as basically just stuff moving through an area, right? If I have a pipe with water flowing through it, I've got, hydraulic flux, right? Something like that, right? Just stuff moving through an area, right? It's the most basic definition of flux I can give. All right, so when we're talking about electric flux when it comes to Gauss's law problems, right, where I was concerned about the amount of electric field, right, passing through some area, right, some surface. Okay, so that's just a pretty darn good image of kind of what we're even like, what this even really means, right? I feel like half the battle in Phys 2 is figuring out what we're talking about in the first place, and the other half is assigning an equation and actually solving it from there. So yeah, these are very, very good pictures to help you get a visual idea about what the heck is even going on. So yeah, so you guys can revisit that later if you have any questions about that. All right, and then I was kind of talked about this just a little bit, but one thing to note is that area vectors are always perpendicular to the surface they described, right? They're always normal to the surface, right? Always pointing straight away from the surface. And if we had an open surface, your direction is ambiguous, right? Because I could have one pointing off the back, right? Something like that. So you'd have to define which direction was positive or negative, right? Something like that. So a little bit more on that in these slides here if you're curious about that. All right, so in Gauss's law problems specifically, right, Nick brings up a good point. So what if the area ain't flat, right? So non-planar geometries, right? So those are going to be your spheres, your cylinders, right? The objects that we deal with Gauss's law, right? We say that there's basically just an infinite number of really, really small area vectors, right? Across each little kind of square in our shape, right? And we can add those up across the entire length or the entire surface of this object, right? And then we can get one area vector that points off of the surface, right? You guys kind of had a couple of text boxes about that in a couple studios ago, right? You guys were going to wind up a piece of paper, and then it was a piece of graph paper, I believe, and there was a bunch of small area vectors, and it asked you the same question. Yes, so yes, we can do that, right? So that's what we do for all of our cylinders and spheres and things like that. Okay, so a lot of words here to describe basically that definition, right? So for our shapes that we care about, right, our cylinders and our spheres, right, you can see there's just one area vector coming off of the surface, right, for all intents and purposes. So let's see. Yeah, so this is a very, very important slide here, something I'm gonna write a little bit of explanation down next to it as well. So when we use Gauss's law in this class, it is very, very, very important that you guys realize that there are two symmetry arguments that we have to make in order to simplify that left-hand side, right, that integral side. Okay, so if I write out Gauss's law again up here, right, I do the surface integral, right, of E dot dA, all right, equal to Q enclosed over epsilon naught, right? So it's very important to realize that as it stands right now, we can't do anything with that left-hand side, okay? We are not equipped with the tools to take a surface integral in this class, and that's not part of the class. Don't worry about that. But so it's important that we get to this endpoint, right? Just E times A here, all right? That's our goal, right? So there's two intermediate steps to get from this integral right here, right, to this final point right here, right? So I will find that the one that most students remember is that E has to be constant. And yes, that is true, right? But if I just look at this integral right now, I can't just pull E out of my integral immediately, right? I can't just do that, right? And the reason I can't do that is because there's a dot product between those two quantities. Those are vectors, right? They're not numbers, they're not scalars, they're vectors, right? So I can't ignore that dot product. So the first thing I have to do whenever I'm faced with a Gauss's law problem, right? First thing I always have to do is to make sure that E field and the differential area vectors are parallel to each other, okay? Because if they aren't parallel, then your life's pretty easy. Then we can't use Gauss's law, right? You move on with your life, you do something else, right? But if they are parallel, right, then that brings us to this secondary step, right? So surface integral of just E times dA now, right? So that's the first step. Those quantities have to be parallel to one another, okay? They have to be parallel to one another, right? And what that looks like, if I was just to draw a sphere in blue over here, right? I have not really correct my terrible drawings, right? And let's say I had a just one charge in the center, right? So we know, let's say it was a positive charge, right? Plus Q. We know that the electric field lines would be pointing straight away from it, right? Because it's a positive charge, right? So that's my E field lines. Right, and then we know from our discussion on area vectors, right, that my differential area vector would just be pointing normal to my surface, right? Any point along this sphere, right, and be pointing off of the surface. So it would look something like that, right? If I just did it in red there, right? So notice how those two vectors are inherently parallel to one another, right? So this will tell you that our spheres are pretty much like the ideal Gaussian like shape, I guess is how I would put it, right? If we have a sphere, we know we're going to be able to use Gauss's law, right? Simply because E and dA are always parallel to one another, okay? So does that make sense, I guess, from a pictorial reference, right? Kind of what those two vectors need to have happen, right, in order to use Gauss's law, right? So that's the first step, right? And I find that that's the one most people forget about, okay? So it's very, very important you guys remember that's the first step. The second step that everybody does remember, right, is from this integral right here. Right, now I am concerned about whether or not E field is constant. If E field is constant, right, I can just pull it out of my integral, right? It's basically like the equivalent of like a 2 or a 3, right? I could just pull it out of my integral and move on with my life. So I would get integral, or E times integral of dA, right? And everybody knows from, I believe it's Calc 1, maybe Calc 2, right, that the integral of d anything, right, is just that thing, right? So I will get to E times A from there, all right? But just wanted to reiterate one more time. If you go straight from here to here, right, you're missing out on a very, very, very important step, right? And so that if a Gauss's law problem ends up becoming a free response question, I guarantee you we will ask you for the two symmetry arguments. I guarantee it, right? They will be worth probably 2 points, 2 or 3 points apiece. I could see it in my head right now, right? So it's very important that you guys remember that those two symmetry arguments are needed in order to use Gauss's law. All right, so I see a question here. How will we know if E field is constant? Well, most problems explicitly state it, right? So that's a very, very good question, right? It's hard to know exactly what's going on necessarily when physics is just, kind of ambiguous, right? So in general, right, the problems that we can use Gauss's law for, right, will be shapes with nice symmetry, right? There'll be spheres, there'll be cylinders, right? And unless I'm forgetting about basic geometry, I'm pretty sure those are the only two we can ask you guys about things related to Gauss's law for. So if you're dealing with either a cylinder or a sphere, right, it will be the case, right? You'll probably just have to draw us a picture, something like what I've already drawn for you, right? And to prove to us that those two vectors are parallel to one another, right? But as far as E field being constant, right, that's another good question, right? And it deals again with symmetry, right? So let's say if I wanted to find the E field at a radius and that dotted line right there, right? It's not a perfect circle because I can't draw, but basically, because I have spherical symmetry, right, the electric field will be the same at every point along this dotted line, right? At every point along this dotted line, meaning at the same radius, all the way around the shape, the electric field is the same, right? So that is basically what you're looking for. And it's the same thing for a cylinder. I just don't even want to try to draw a cylinder because I'm going to jack it up even further. But that's kind of what that visual looks like, right? The electric field is the same right there as it is right there, right? Because those are the same radius away from one another. All right. So I hope that answers your question. Awesome. Thank you, Kevin. All right. So next question. So, Catherine, that's a very, very good question. And I will actually, no, that's a very good question. So I'll say, so we talked about polarization or how a charge resides in an insulating conducting sphere. We haven't talked about polarization. Yeah. So the topic of polarization is not something you'll be required to know. And in fact, I'm very impressed that you asked that question. Polarization, no. But the difference between a non-conducting and a conducting sphere, however, is a very good question, and you will probably deal with one problem one way or another, right? So let me cover that real quick. That's a very good question, Catherine. Thank you. But before I cover that, does anybody have any questions about these two symmetry arguments here? Probably the most important part of Gauss's law, if I was to summarize it, right? Feel free to unmute yourself or say something in the chat if you have a question about this specifically, because it's very important. Okay, I will take that resounding silence as a we're good. Cool. So yeah, so Catherine asked a very, very good question, right? So basically, what's the difference between a non-conducting and a conducting sphere, right? Definitely something I didn't understand when I was in the class, so very, very good question. So let me draw a non-conducting sphere right here in red. Oops, if my circle would correct, there we go. All right, so I'll say NC for non-conducting, right? And then a purple for conducting. All right, so conducting. All right, so let's start with the non-conducting example for a change, right? So when I have a non-conducting sphere, right, or a non-conducting object in general, right, that just means that wherever charges were at the very, very beginning, that's where they're going to be at the end of time, right? So you can think, for all intents and purposes, you can think about this shape kind of like a tennis ball, like a rubber racquetball sort of thing. If I've got a bunch of charges in here, right, just spread out, doing their thing or whatever, right? Wherever they're at right now, they are never going to move from that spot, right? They're stuck in place, okay? So as far as Gauss's law is concerned, right? If I were to draw, let's say I wanted to find the E field at that blue radius right there, right? I would have some charge enclosed in there, right? Notice how there's quite a few positive charges that are just kind of chilling around in there, right? And there'd be a bunch more, right? But, excuse me, but my point is, for a non-conducting sphere, right, you can calculate the electric field anywhere, right? It won't be zero at any point unless you go like way out to infinity, right? Which we'll never do that, right? So you can count the electric field inside or outside the sphere, right? That's very important. Whereas on a conducting sphere, for example, right? I don't know why you would, I guess, think about like a Van de Graaff generator. I don't know if you guys saw that, and you should have seen it in lecture, but it's basically like this tower looking thing with a ball on the very top, and your instructor should have probably gotten like a wand and like brought it close, and there was some movement of charges from the wand to the Van de Graaff generator. Super cool stuff, but basically that's what we're dealing with here. So in a conducting sphere, right, you have charges centered kind of all around the surface of your sphere, right, or your object, right? There is none within the confines of the shape, right? They're all on the surface, right? Because they're free to move, right? In a conducting object, their charges are free to move wherever they'd like, right? So if I brought say that negatively charged wand near this, right? I'm just going to draw a terrible looking stick, right? Say that was negatively charged, right? Some of those positive charges, right, will be attracted to this wand, right? And they'll start to move off of the surface and get on that wand, right? So my point in drawing this is that notice if we were to try to find the electric field in here now, right? Notice how there's no enclosed charge in here, right? Nowhere in here do I have any charges, right? So the electric field inside of a conducting sphere is 0, right? Simply because I have no charge enclosed, right? The entire right-hand side of Gauss's law is 0, right? So electric field doesn't exist, all right? But if we were to move outside the sphere, right, in this orange electric field, right, say I wanted to find it there, right, now I'm enclosing all of these charges, aren't I? Right, so now I can calculate an electric field because I've got some enclosed charge. Okay, so that's kind of how I would separate those two, non-conducting versus conducting, right? It's basically about whether or not I'm enclosing any charge or not, right? So make sure to go through those sort of mental gymnastics, right, before you start a Gauss's law problem, right? But very, very good question. Sorry, that's kind of a long-winded answer, right? But does that make sense, it seems like? Does the concept of no electric field inside a conducting sphere apply to cylinders and other shapes? Absolutely, right? Anything that's conducting, those charges are always going to appear on the surface, right? So very good question, good job. All right, Nick, thank you for answering that other question, right? So just one more recap before I go on. All right, two symmetry arguments, right? The area vector and E-field vectors have to be parallel to each other, right? That is the first step. You cannot swap the two steps, right? Those two vectors have to be parallel first, right? Before you do anything else. And then the second one, right? E-field is constant at the same radius, at every point along the same radius in my shape, right? Whether I've got a cylinder or a sphere or some other weird geometric object, I can't think of it right now, right? So very good. Glad that we got to cover those two arguments, right? So if you have any more questions about those, feel free to send us a message or feel free to unmute yourself, that sort of thing. Okay, so because it seems like the Gauss's law problem or the Gauss's law response is the most popular on the poll, I don't think I'm going to do this example right now. We could do it when we've got some time to do examples, right? I just don't want to lecture for more than is necessary for everybody else, right? So I think I'm going to skip this example. We can go through it, right? Or we can go through whichever other example you guys want, right? But this one was actually on your studio from last Friday, I believe, or maybe last Wednesday. You've done this before, that's all I'm saying. All right, so I will kind of skip through this for now. Like I said, we can come back to it. Don't you worry, we can come back to it. And then, yeah, so it looks like we're just doing this example here. Cool, yeah. So like I said, we'll go through that example when the time comes, right? So at this point, my spiel is sort of over, so I'll hand it off to Nick. But before I go, right, does anybody have any more lingering questions about symmetry arguments, Gauss's law as a concept, right? Not necessarily solving a problem for it yet, right? We'll get there. But anything conceptual wise, like these pictures that I drew, things like that, right? You guys had some great questions so far, so feel free to ask any more. I'll wait a few seconds. Okay, all right. So it seems like you guys are good there, so I'll be looking forward to that. Other than that, okay, so here we go. Well, we have to be able to say what kind of symmetry different things have. That's a good question, Sarah. And I would say maybe if the Gauss's law question is a free response question, it'll basically just say like, hey, I guess what type of symmetry is this, right? And if it's a sphere, well then, right, fill in the blank, right? Spherical symmetry, right? So if we do ask you that, it'll be kind of like oh, duh, right? It's a cylinder, so it's going to have cylindrical symmetry. Something pretty much that straightforward, right? But you'll be required to say what the two arguments are, right? If it's a Gauss's law problem, I guarantee we will have that question, right? So you could say cylindrical symmetry and then blah, 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 these two things, right? That sort of thing. Does that answer your question? Awesome. Cool. All right. At this point, I will hand it off to Nick. I'll shut up for a little bit. Wait, sorry. Never mind. One more. What do we do for Gauss's law if some dA vectors of this shape are perpendicular to the E vectors? I'm assuming you're talking about a cylinder, right? Where I guess you'd have some points along that shape would be perpendicular to it, right? And really that gets, okay, good, yeah. And so really that gets simplified in the sense that we don't care about what's going out of the two end caps, for example, right? We're only concerned about the tubular part of it, right? So where the E field and the area vectors would be parallel, that's all we're concerned about. Does that make sense, Tristan? That's a good question. Cool. All right. Yep. Sorry, I will shut up now. Nick, the floor is all yours. Let me stop sharing real quick.
You're all good. Yeah, just to build on that question, if the surface that we're considering is perpendicular to the E field, then there's no flux going through it, as per the definition of flux, because it's a dot product. But yeah, that answers everything. Let me figure out screen sharing. Okay, can everyone hear and see my screen?
Yeah, I can see it, Nick. You're good.
Okay, cool. And that's the worked example. Okay, so the last topic in block 1 is electric potential, and I won't lecture too long about this because we didn't cover topic 1F yet. We only covered topic 1E. So I'll just try to stay as quick as possible. But in short, electric potential V is a scalar that tells us how much energy something has per unit charge. So a really important equation that comes up all the time is delta U is equal to Q times delta V. That's on your equation sheet, and you use it again and again and again. Basically, it's just telling us the relationship between potential and potential energy. And that's another distinction that I want to make sure everyone gets a good grasp of, because electric potential, that's usually denoted V, that's the voltage. Whereas potential energy, that's U. So for instance, if I have 2 point charges, the potential energy of those 2 point charges is going to be just K, Q1, Q2 over R. Whereas a single charge by itself, that's going to set up a voltage equal to KQ over R. I need 2 charges in order to have potential energy between them, whereas I only need 1 charge to set up a voltage. And this is sort of analogous to potential energy from Phys 1. So like I know from Phys 1 that if I have 2 massive bodies, M1 and M2, then they have some potential energy of interaction. And the equation is actually very similar. It's U is equal to big G times M1 times M2 over R. But there's no real analogy to voltage I can think of in Phys 1, unless someone has one. But yeah, that's sort of what voltage is. Let's see. So voltages obey the superposition principle. So just like I said earlier here, a single charge just by itself is going to set up a voltage equal to KQ over R. But if I have multiple charges, all I have to do is add the voltages from all those charges, and that gives me the voltage at any point in space. So the equation I have here on the left, that's my discrete case. If I have n discrete charges, I just add up all their voltages. And if I have some continuous distribution of charge, I integrate. Sort of similar to what we did with Coulomb's law, but usually voltages or integrating voltages is easier because we don't have to worry about R vectors. And the reason is because voltage is a scalar, whereas electric field is a vector. So I only care about the magnitude of the R vector, not the R vector itself. So let's see an example of that. Let's suppose I had a semicircular arc with radius R, and there's a non-uniform linear charge density given by lambda equals A times sine theta. So A is just some positive constant, and theta is measured from the positive x-axis. So lambda equals A sine theta. If I plug in 0 for theta, that means I'm right here. I have little charge here, and then as I move around the circle, I gain more and more charge, accumulating to a maximum right here, where sine of pi over 2, or sine of 90, is 1. So that's where I have the most charge, and then I again have very little charge over here because the sine of pi, or sine of 180, is 0. But we don't have to worry about how the charge is distributed too much, because we can just pretty much plug and chug for the equations. Assuming the potential is 0 at infinity, what is the total electric potential at the origin due to this charge distribution? So we just take that equation above. Again, it's a one-dimensional charge distribution because the charge is distributed along a line. That line is curved, but it's still distributed along a line. which means that dq is equal to lambda dl. Lambda is given, and dl for any circular shape is going to be r d theta. And unlike the electric field problem that Kate showed earlier, I don't have to worry about the r vector because, again, potential is a scalar, not a vector. So instead, I can just say that this little r that appears in the bottom, in the denominator here, that's just the distance from the source, which is this line of charge, this arc, to the observation point, which is at the origin. Cool. That pretty much sets up our integral. We can just plug things in. For little r, we just put it in big R, and then we found dq. We integrate from 0 to pi. The reason why we integrate from 0 to pi is because the bounds of integration are always the smallest and largest values of our integration variable. Since we're integrating with respect to theta, we start at 0 because we started at theta equals 0 over here, and we end at pi because that's where our arc stops. Cool. And that gives us the potential at the origin. All right. So something that's really important in the broader context of electrostatics is the relationship between potential and field, between voltage and field. And the equation to remember is that electric potential and electric field are related by a derivative. So if I want to know the x component of the electric field at some location, I just have to take the negative derivative of the voltage with respect to x. Or more generally, if I want to know the electric field, like the full vector form, the I hat, j hat, and k hat, I just take the negative derivative of the voltage with respect to x, y, and z respectively. So a place where we can see that is for point charges, for instance. We know that the voltage set up by a single point charge is kq over r. If I take the negative derivative of that, that's just taking the negative derivative of kq over r, which gives me negative kq over r squared. And that, the two negatives cancel out, and that gives us the radial component of the electric field made by a point charge. And that's a nice transition into this handy chart that I made here. There's 4 variables that we have to sort of consider in electrostatics: force, energy, potential, and field. And this is how we convert between all of them. So I guess we started at topic 1a, we started with electric force. So if 2 charges, for instance, are separated some distance r, then the force on those 2 are, the force of interaction between those 2 charges is kq1, q2 over r squared. If I want to find the electric field set up by a single charge, all I have to do is divide by q, because I can't have a force if I don't have more than one charge. Just a single charge by itself sets up an electric field. And that equation for electric field is kq over r squared. If I want to convert field to potential, all I have to do is take a derivative. That's sort of take an integral. That's topic 1F, I think, deals more with this. So that's something you'll see in Friday's studio. But basically, if I want to find the change in potential, I take the negative integral of E dot dl. So the negative line integral of the E field over some distance, and that'll give me a change in voltage. And as we saw earlier, if I have the voltage and I want to find the E field, I just take a negative derivative. For those of you who haven't had Calc 3 yet, or in Calc 3 right now, this negative, or this upside down triangle is just called nabla. It basically says take the derivative with respect to each part. But all you have to remember for that test is this equation right here. The simpler case of the electric field in one direction is the negative derivative with respect to that part. And then if I want to convert potential to energy, all I have to multiply is by Q. This is another super important equation that I mentioned on the equation sheet earlier, delta U equals Q delta V. We use that all the time. And then we can convert between between energy and force using analogous relationships.
Was
there a question there? Okay, thought I heard something, but there's a question, just let me know. Cool. Okay, one more quick example. All right, so this is just telling us, suppose the electric potential in some region of space is given as just some function of x, y, and z. Again, it's a scalar function. It doesn't have I hat, j hat, and k hat components. It's just some number, basically, that I plug in x, y, and z coordinates into to get a potential at some point. And now I want to figure out what the z component of the electric field is. So if I have my E field, I just take negative derivatives to find voltages. So the z component of the electric field, I take the derivative of this function with respect to z, and I get this. So I would just plug that in wherever I want to figure out what the electric field is. Okay, last topic that I'll touch on is visualizing electric fields and potentials. So a term that's used all the time in electrostatics is the term equipotentials. And that just describes any region in space, any line in space where voltage is constant, kind of like contour lines on a topographical map. Those represent areas of or lines of constant elevation. Equipotentials are sort of the same thing, just regions of constant voltage. And there's a phrase that helps me out a ton when I'm thinking about potential and fields. Electric fields point downhill with respect to voltage. So if you've had me in studio, or if I've helped you in studio or homework, you've probably already heard me say this because I say this all the time. It really helps to visualize electric fields and voltages if I just repeat to myself, electric field lines point downhill with respect to voltage. But that phrase by itself is a little bit abstract. So let's see what that means. Let's say I have a dipole, and that dipole just consists of some positive charge here on top that's creating E field lines coming away from it, and a negative charge here on the bottom that's bringing E field lines in towards it. A dipole, by the way, is just a positive and negative charge separated some distance. Really nothing more than that. So that's the field. We sort of know what the field created by a dipole looks like. What's the potential going to look like? Well, again, if we think about the phrase electric field lines point downhill with respect to voltage, we can think of the positive charge as a hill. We can think of this positive charge right here as sort of just like a big hill in elevation, and this negative charge here as a valley. And then these contour lines, or they'd be contour lines if this was a map, but these equipotential lines just represent regions of constant voltage. And notice how the hill sort of goes up and it peaks at this point charge here, and then this valley goes down and its minimum is at this negative charge right here. Well, the electric field lines pointing downhill with respect to voltage, that just means that these electric field lines, they're always normal to these contour lines, to the equipotential lines, and they're just moving down in elevation, if you will. They're moving from this hill down to this valley, terminating at the negative charge. And that's the negative sign in the equation E equals the negative derivative of V. That's just telling us that the electric field lines are going to point downhill with respect to voltage. I think that's all I wanted to say there. Oh yeah, if one more thing I'll mention is that if you've had, or if you've seen these from Calc 3, or if not, you will be seeing them soon. But the reason why electric potential lines or equipotential lines are normal to electric field lines, why every single intersection that I see here is a 90-degree intersection, that comes from, again, the definition of, let's go up, this definition here, that electric field is the negative gradient of potential. This just tells me that this vector right here can be obtained by taking the gradient, the negative gradient of this function, which gives me a vector that's normal to the potential lines. I think that's it. Okay, and I wasn't watching the chat, but it looks like Tyler's taking care of it. Okay, so now I'll just open up to everyone. Is there anything that I didn't explain sufficiently well or need to go back over? Feel free to unmute yourself or to speak up. And Tyler and Kate, if you have anything to add to what I mentioned.
Nope, Nick, looked great to me, man. I was just going to introduce next, I guess, the process for our examples, but I don't have anything else. That was great.
Awesome.
As far as that question in the chat goes, we do not post the rubrics to those free response problems. Again, because they have the potential to be used in future exams, so we don't want to give you the solution for those. But anytime you stop by office hours or email any one of us, we're more than happy to work through those with you. That's not a big deal. We just don't want to make the rubrics public. Okay. So as far as what you guys voted on, right? Gauss's law won by a small amount, right? Closely followed by electric potential, and then electric flux was beyond that, right? So we can definitely go through a couple of each of those problems. I have a couple of Gauss's law problems prepared already. So Nick, if you don't mind, I think I'll just go right into those, and then I'll pass it off to you for potential again. That sound okay to you?
Sounds good.
Cool. All right. Awesome. So if everybody wants to navigate there, I chose two problems from homework 1D, right? The first one was that non-uniformly charged cylinder problem, and the second one was that non-conducting sphere problem, right? So I'll start with the cylinder, right? And I'll give everybody a second to get there. Again, it was on homework 1D and the non-uniformly charged cylinder 2 problem. All right, so share my screen here real quick. All right, we will go through that. All right, so let me just make sure that I can see that. Yep, cool. Okay. Yep. So like I said, just to reiterate one last time, right? Homework 1D, non-uniform charge cylinder, right? Just so you can get on the same page with me here, right? So this problem, right? We're looking at an infinitely long solid cylinder, right? Some radius has a non-uniform charge density, right? Where rho is that equation, right? And we want to know the magnitude of the electric field at some distance less than my total radius, right? So what helps me personally before I do anything else is just to draw a picture of whatever shape I'm working with, right? So in this case, we've got a cylinder. So I'm going to do my best to try and draw one of those, right? So yes, that's what I wanted, a square. There we go. Cool. We'll do something that looks like that, right? And so my charge density is non-uniform, right? So I can't say that the charge per unit volume is the same everywhere, right? But I know that there's some electric field being produced by this object, right? Because it's got some charge density, right? So if this radius of this cylinder is big R here, right? The total radius, right? I'm looking for the electric field at a radius less than that, right? So kind of somewhere in here maybe, right? So that would be my Gaussian surface, right? That orange one there, right? So I'll call that radius over, I guess here, right? I'll call that one, no, whatever. I'll call that one little r, okay? So now that I've got my picture, right, to figure out what the heck's going on, right? First thing I want to note, right, is that I'm not enclosing all of my charge, right? And because it's a non-uniform charge density, I know I'm going to have to integrate, right? So the reason I chose this problem is because it's going to require a little bit more work than your average Gauss's law problem, but that's a good thing, right? Because free response questions usually aren't uniformly charged things, usually, right? So let's do it. Let's write out Gauss's law first, right? Always a great place to start, right? And please, I just want to point out, please, if we ask you to write out Gauss's law, please don't write out Coulomb's law. On the equation sheet, it specifically says what the laws are called, right? All you have to do is read them, right? You would be shocked as to how many people we get put Coulomb's law down for that, right? And while it is theoretically possible to solve the problem with Coulomb's law, just don't do it, right? It's honestly kind of a funny thing that it happens, right? So if we ask for Gauss's law, please actually write out Gauss's law, right? That's step one, right? So I'll write that out right here, right? Surface integral of E dotted with dA, right? Equal to Q enclosed over epsilon naught, all right? So whenever I'm faced with a Gauss's law problem, right? And after I've written out what Gauss's law actually is, right? I always like to start with the charge enclosed, right? The right-hand side of the equation. Because I know if we're using Gauss's law, that left-hand side is going to simplify to E times A. I know it is, right? I just have to prove that to whoever's grading it, right? So I'm going to start with the right-hand side because I think that's the sort of the harder of the two things to figure out, right? So I might as well get that over with, okay? So let's start with charge enclosed, right? We're going to figure out what that term is, okay? So remember, charge enclosed in its most basic definition, right, is the integral of dq. Right? And so I would recommend in any Gauss's law problem to always start with the integral of dq, right? Even if it's a uniformly charged cylinder, if you start with the integral of dq, you're never going to be steered wrong, right? You'll always end up with the right answer. Whereas if you assume you don't have to integrate, right, and it's a non-uniformly charged object, that's going to come back and help you lose a few points there, right? So just make sure to always start with the integral of dq, right? If it's easier, it'll simplify. If not, then we'll have to take an integral, right? But not the end of the world. Okay, so remember, right, dq, right, has three different forms based on the dimensionality of the object that you're working with, right? So I'll write those out kind of in, I guess I'll do green over here, right? So for one dimension, right, it would be lambda dl. All right, use that mostly for Coulomb's law problems, right? One-dimensional charge densities. Okay, two-dimensional, right? Sigma dA, right? Sigma dA, and three-dimensional. Sorry, I can't talk. Is going to be rho dV. All right, so it's important to remember that whatever object you're dealing with, right, you have to have the correct symbology, right, to go along with that, right? If I were to use sigma dA here, right, that'd be a problem. Okay, so obviously I've got a three-dimensional shape because it's a cylinder, right? So I'm going to be working with rho dV, right? And this problem's kind of given it to you because it says volume charge density rho, right? So that's pretty straightforward, right? But usually in the first response question, it's not always that simple, right? So just wanted to point that out, right? But on my version of the problem, my rho is 4r cubed, right? That's my version of the problem. I think that log kappa may generate random equations, right? So just keep in mind that's my rho, right? And then dv, right, was always kind of a point of confusion for when I was a student, right? But in reality, it's just the derivative of volume with respect to the variable that you care about, right? So to start out, I always like to just write out what volume is, right? Volume of a cylinder is going to be pi r squared L that Cade talked about earlier, right? And so if I know volume, I can get anywhere I want, right? I can just take a derivative to get to dv, right? And that would be 2 pi RL dr, right? Don't forget about that dr, right? I don't know what r is, right? R is variable because I'm integrating with respect to it. So it has to be a differential there on the end, okay? So dr. So now that I've got dv here, well, I know that dv belongs right there, right? So I've already got it written out, so that makes my life easy, right? A little bit earlier, we had a question about when to use the Gaussian radius versus the total radius, right? That's a very, very, very good question, right? And Nick answered it beautifully. I think I just wanted to repeat that, right? On the left-hand side of Gauss's law, right, this integral, right, is always dealing with your Gaussian surface, right? So no matter what, on the left-hand side, that's r sub g, right? That's your Gaussian radius always, right? On the right-hand side, right, it can change, okay? So it changes based on how much charge I actually have enclosed, okay? So if I went back to my picture here, right, notice I am at some point inside of this total cylinder, right? So I've got some amount of charge that is less than the total, right? So it wouldn't make any sense for me to use big R here, would it, right? Because big R implies that I've got all the charge, right? So in this case, I would use little lowercase r, right? Because that's the radius at which I'm trying to figure out the electric field. So I've only got that much charge to work with, okay? But that would change if my electric field, if I wanted to find the electric field, let's say out here in pink, right? Say I went all the way beyond my cylinder, right? Wanted to find it out here. Now from here, right, I would use still on the left-hand side, it would be my Gaussian radius always, right? But on the right-hand side, I would use big R, right? Because I can't have more charge than exists, right? I've just got all of it that's in blue right there, right? So I've got all this stuff, right? All that orange plus all that blue, right? Hypothetically, that's not what the problem is asking for, but just letting you know that's where those two would differ, right? So always keep in mind how much charge do I have and where am I at on this shape here, right? Because it can change. It's one of the easiest things to change for us being on the instructing part of the instructing side of the class, right? It's super easy to change where we want you to find the field, right? So just make sure you know that, keep that in mind, okay? But in this case, we're trying to find it at that orange R, so I will erase all of this other stuff so as to not confuse people, okay? Get rid of all that. That's fine, it's not worth it. Okay, cool. So if I were to rewrite this integral, right, in terms of things that I actually care about, right, the integral from 0 to lowercase r, right, my Gaussian radius of 4r cubed times my dv, right, would be 2 pi rl, and let me move all this stuff over, 2 pi rl dr. Right? So from here, notice that I'm integrating with respect to r, right? So some of you are probably thinking, okay, well, what on earth do I do with that L, right? Remember, if I'm not integrating with respect to it, I really don't care what it is, right? It's a constant for all intents and purposes. So ignore that for now. It'll cancel out later, assuming you did all your other symmetry arguments and things right, okay? So I'm gonna integrate with respect to r in this case. So I will pull out everything that's a constant. So 2 times 4 times pi times L out here, right? Times the integral 0 to r of r to the 4th dr there. Okay, right? And so obviously we can all take this integral, right? It's going to be, we'll do an 8 pi L out here, right? And that would be times 1/5 r to the 5th, right? And obviously no plus c because we've got a definite integral. So that's what I get when I integrate to find my charge, right? This is just my charge expression, charge enclosed, right? Once I've gotten to this point, I say pause on your problem, right? And then now we'll simplify the other side, the left-hand side, right? Because the left-hand side, if we do it right, will result in some terms that will cancel out with this charge, right? So that's what I like to do. I say pause on the right-hand side, and we'll go now to solve that integral side, okay? So, right, we know that we can't just straight up take that integral, right? That should have been very, very well covered by now, right? But remember, I got to make my two arguments, right? So one, right, r, e, and dA parallel, right? That 11 looking thing, right, is supposed to mean two parallel lines, right? So let's look at it, right? I've got a cylinder, right? So I know I can work with cylindrical symmetry, right? And cylindrical symmetry says that I've got my dA vectors pointing straight off of the surface, right? And I've got a positive charge density, right? Positive charge density means positive charges, right? And we know positive charges make E field lines that point away from them, right? I'm running out of colors here. Let's do bright yellow, why not? So E field lines would point straight off of that surface, right? Where those charges are originating, right? So yeah, that yellow is awful, sorry about that. But we can see clearly, right, that those two vectors are parallel to one another, right? So there we go, there's my first argument, right? So yes leads to integral E dA, right? Cool, now I've got step 1 of 2 done, right? The next one, everybody's favorite, right, is E field constant at every point along a certain radius in my shape, right? So I'll just write that out as is E constant. All right, so now I'll go back up to my picture again. All right, I'll erase these god-awful yellow vectors. Get rid of that. All right, so basically my question to you is the electric field at the top of this cylinder going to be the same as the electric field on the bottom of this Gaussian cylinder that I've drawn, right? And the answer to that would be yes, right? Because I've got cylindrical symmetry, right? So I've basically got a circle extended infinitely, right, in that direction. So the E field anywhere along this circle, right, which means anywhere along the confines of this cylinder, right, is going to be the same. All right, so E is constant at every radius within my shape. Again, so now say yes again. All right, so now I can just end up with E integral dA, right, which just is E times A there. All right, so once I've proven this to myself, right, my life gets a lot easier. If you are actually integrating to find area, you got off on the wrong foot, right? We should never actually have to integrate the area expression. And what I mean by that is you should never be integrating 2 pi RL, right? It'll just exist as an area from this term right here, right? So that right there is going to be E times 2 pi RL. Okay, so with that being said, right, I will write it out over here, right, on the right hand side. So now I've established I've got E times 2 pi RL is equal to, right, this expression for charge enclosed, right, the one I just found. Right, so I'll write it as 8/5 pi L r to the 5th. Okay, and now that's divided by epsilon naught. All right, so from here, I'm going to move my other work down because I don't have my room. All right, and then I'm going to divide over my area, right, and see where that gets me. So E is equal to all this garbage I just wrote out. All right, and then if I were to extend this line here, right, now times 2 pi RL. All right, so now from here, you can see kind of why I would refrain from simplifying things further in the numerator, right, because some nice things cancel out. Right, so right off the bat, the most important part you should notice is that the length cancels out. Right, and that's a good sign, right, because we're not even given the length of our cylinder, right? And that plays into the fact that we need to have cylindrical symmetry, which means it's infinite in length. Okay, so if length cancels out, we're doing something right. Right, now pi's cancel, great, right? And r to the 5th becomes r to the 4th because I've got 1 r right there, right? And obviously 8 divided by 2 becomes 4. right? So really my final answer, right, is honestly a lot simpler than this, right? Becomes 4 r to the 5th over 5 epsilon naught. All right, and that's all there is to, whoops, sorry, r to the 4th. Thank you. R to the 4th over 5 epsilon naught. All right, and just to check my notes, yep, that is right. I didn't make any algebra mistakes. All right, so does that, let me go back to Zoom because I'm not actually looking at it. Does that problem solving process make sense? I see a lot of questions here, so it looks like a lot of people kind of got them answered. I will say this last one. So how would it change if it was uniform? Right, so good question, Sebastian. If it was a uniform charge density, right, it would be uniform charge density. I wouldn't have had to integrate in the first place, right? So right here for my charge, I would have gotten integral of rho dv, right, where rho is a constant now, right? So now rho could be factored out of that integral, right? And I would just end up with the integral of dv, which would just be v, right? So rho v, right? Does that make sense? Why it would change if it was uniform? Good, good. Yes, thank you. Yeah, very good question, right? But again, to revisit my point, if we are always going to start with a DQ, right? Because it'll never ever steer us wrong, right? If we started with just rho v in this problem, we would automatically be shooting ourselves in the foot, right? Because that would be an automatic, we automatically get it wrong. Okay, so good question there. So got a question about why exactly is the rho we use based on little r and not big R? So Zach, to answer your question, that's because the rho in this problem was given as c, or like 4 times little r cubed, right? Where that little r is the variable radius, right? As you move from the center of the cylinder to the outer edge, right? So that was just given to us, right? But that's always going to be a variable r, right? So a lowercase r, not big R. Does that make sense? Cool. All right. I got a question from Kaylin. So we're asked to explain the 2 steps needed to get to E times A. All right. How much detail we expected to provide? Very, very good question. All right. And Kaylin, to answer your question, I would say basically exactly what I've got here. Right. So you could say, you could draw those 2 vectors, right, that I had drawn out in terrible colors, right? You would do that and say, hey, these 2 vectors are parallel to one another, right? Basically combine the picture that I drew with the words that I was saying. That's exactly what we're looking for, right? So I would ask yourself pretty much these 2 questions here, right? Are these 2 things true, right? And then find your supporting evidence to make sure that you could prove that, right? Something like these little X's that I've drawn, right? Drawing those 2 vectors parallel to each other. That's the sort of explanation we look for when we say, yeah, how do we know that the symmetry arguments apply? Does that make sense? Cool, awesome. And question from Justin here. So if the Gaussian cylinder is bigger, would you use the Gaussian radius? Right, so again, the left-hand side, so think about it in terms of left and right-hand sides, right? The left-hand side being that integral side. The left-hand side is, is always your Gaussian radius. Always, always, always your Gaussian radius, okay? So don't even think about the left-hand side. It's always R sub G, okay? The right-hand side will only be the radius of your object, right? If you're asked about the electric field at a point that's outside of that object, right? So again, if I was to draw this pink Gaussian surface way out here, right? Right. Notice how I'm enclosing all of my charge now, right? I've got the entire cylinder in my Gaussian surface, right? That point I would use big R in my charge expression, right? Because I can't have more charge than exists, right? So the charge is confined to those 2 bounds, right? 0 to big R. Does that make sense, Justin? Cool, awesome. I can see the sort of metaphorical light bulb going off, so that's good. All right, so very, very good questions we have here. Does anybody have anything else about this particular problem, right? What's going on, how I did anything, right? Yeah, so this problem has every right to be a free response question, right? We would pretty much ask you exactly what I did here, right? It'd ask you for the charge expression first, right? The 2 symmetry arguments after that, probably some picture as to what the Gaussian surface looks like, and then the final E-field expression. That's pretty much how a free response question would go if this was the topic, for example. Okay, so so if you have any questions about this process, right, speak up now or forever hold your peace, sort of thing. Okay, but I feel like that's fairly straightforward. But If you guys have any more questions, right, feel free to send us an email, ask questions, things like that. Is the test not done the same as it was done in Physics 1? So it'll be very, very similar to it in the sense of where we will have 16 multiple choice questions, each worth 5 points apiece, right? And then a 20-point free response question, right? So only out of 100, not 105, right? So no extra credit, unfortunately. But those that free response question will look very, very similar, right? It's that structured approach, right? We ask you to do one thing at a time, right? And we won't dock you off for multiple things ever, right? That's double jeopardy. We don't do that, right? So as long as you can, basically, as long as you can do exactly what I walked through here, right? There's no reason you should get anything less than like a 15 or a 16, right? Barring algebra or calculus mistakes, right? It's going to be structured pretty much exactly how I solved it. Okay. So I've talked for a while, so I'm going to pass the torch on for a electric potential question. But if we have time at the end, we can come back to another Gauss's law problem, right? And I'm happy to do this anytime, right? Send me an email, do whatever, right? But I will go get some more water in the meantime. So Nick, I will pass it off to you at this point. You ready to go with an electric potential problem?
I think so. I sort of went over some when I was doing my spiel, but I don't know. Like topic 1F is obviously not on the test, and I did the ones from topic 1E. I can go over them in more detail, but if people want, I can go over something else because I don't think that's going to be highly testable. I don't know.
Yeah, I agree with you. I would say the only one that to me was interesting was either the asymmetric line charge voltage from homework 1E, where you get some integral stuff in there, or kind of one of the ones we worked on in studio, right? But it's totally up to you. I don't mean to dictate, but that's all I had in mind.
Okay.
Yeah. So I'll let you decide, but I'm gonna go get some more water. I'll be right back.
What does the chat think? Should I do potential or something else?
If you have any potential problems.
Okay. Let me hunt for some. Give me one quick second. Sorry, this is embarrassing. I should have had it pulled up earlier. Give me one quick second. And I'm going to do the question live. That way it's more sort of real. So give me a quick second to get logged into on Kappa. I'm sure everyone is not terribly opposed to a break. So okay, while I'm waiting for long Kappa, just looking at the chat, error analysis, we can definitely do that. Can you go over how to determine which direction the electric field points? Sure, we can definitely do another Coulomb's law problem after this, if that's what you meant. And when will the room assignments be posted? I don't know too much about the logistics of the exam. Hopefully soon, because the test is on Thursday, but that's a question for Todd. Or Dr. Ruskell, excuse me. Almost done pulling up the question. Okay, here's a question. Let me share my screen. And this is from the final exam practice problems, but the final exam is cumulative, so this is just something brand new that will come up again. Let me make this bigger. There, oh, too big. A little bit smaller, there we go. Okay, charge of an electric particle. So a positively charged particle has an initial kinetic energy of that many joules, and it then enters a region of space where the electric potential changes by an amount delta V. the voltage is decreasing in this region and exits with a final kinetic energy of something else. What is the charge of the particle? Okay. The first step when I'm doing any physics problem in Phys 2 is to identify what equation this is, or what's the governing equation? What's the governing principle? We see that kinetic energy is changing. It starts with some kinetic energy and then it exits with a different kinetic energy. And we're also given some sort of voltage. Well, we already know that voltage can be converted in back and forth between energy using the equation delta U equals Q delta V. And since we have energy, then this is probably going to be, well, this is definitely an energy problem, but it's safe to use the conservation of energy here. Or it's safe to say that to approach this problem, we're going to be using conservation of energy because the total energy of the alpha particle must be conserved. So immediately I can say that whatever change in kinetic energy this alpha particle has must be attributed to a changing potential energy. And if its potential energy is changing, and I know I have the equation delta U equals Q delta V, I can just apply that equation to find what the charge of the alpha particle is. So now let me open this up. Shoot, right here. And let me zoom in. Okay. All right. So just to rephrase the question, a positively charged particle has an initial kinetic energy of Ki, and it then enters the region of space where the electric potential changes by an amount delta V. The voltage is decreasing, and exits with a final kinetic energy. What is the charge of the particle? Like I said, we can use conservation of energy. We know that has to hold for just a particle moving in space. So we can say that its initial energy is equal to its final energy. And then its initial energy will have some kinetic energy and some potential energy. And it also, when it exits, it has some kinetic energy and some potential energy. We know what both of these values are. We know what the kinetic, initial and final kinetic energy is. So if I sort of play with this equation, and I rearrange it such that I have U final minus U initial, because any change in the quantity is going to be its final value minus its initial value. I can rearrange this to say that delta U is going to be equal to its kinetic energy when it starts minus its kinetic energy when it ends. So just if I flesh that out in more words, whatever kinetic energy the particle gains must come from a corresponding decrease in potential energy. In other words, what I'm saying is delta K equals negative delta U. And we just invoke that super important equation, delta U equals Q delta V. We know what the change in voltage is. We know what delta V is. We're solving for Q. So if I already have this equation from basically the conservation of energy, or if I already have delta U equals negative delta K, I can just plug in delta U instead of, I can plug in Q delta V instead of delta U. And that gives me this equation. And then solving for Q, I find that its kinetic energy, its charge is this. And I promised I'd do this question live, so let's plug in numbers and make sure that works. Desmos.com. Let's make this bigger as well. That should be big enough. So initial kinetic energy is, let's see, 2.82 times 10 to the negative 12th. Its final kinetic energy is 1.22 times 10 to the negative 12th. Negative 12. And then what else are we given? We're given the voltage change. Delta V equals 5 times 10 to the 6th equals 5 times 10 to the 6th. So the equation that it came up with, the final algebraic answer was Q equals Ki minus Kf over delta V. Ki minus Kf over V. And I get 3.2 times 10 to the negative 19. That makes sense. Charges of particles by themselves are usually pretty small. Where's line cap? Here it is. 3.2 e negative 19 coulombs. Cool. Any questions about that? Yeah, just like I said earlier, I don't think you will really see more on topic 1E stuff other than possibly that example that I just did, or the two potential things or potential examples I went over in the slides, where we have like a shape and we need to integrate to find the potential at the origin. And what else do I do? Shoot, I can't remember. Oh, that's right, where we're given some potential function v of x, y, and z, and then we have to take a derivative to find the E field. It shouldn't be more complicated than that for the test. Cool, so I guess we can start doing, or I guess Tyler, what's next in the poll, and then maybe we can do the.
Yeah, exactly. Thanks for remembering. I was just gonna say the same thing. So electric flux problems was the next one that had an absurdly high number of votes. So I have just a quick one of those that we can go through, and then we can open up the floor from there. I'm more than willing to stay after. I don't mind at all. So I will do an electric flux problem. It looks like. And to
I have one written out neatly if you want.
Okay, I pulled one up in the from the exam review problem, so I think I'm okay. I did want to say just one more time, guys, I did put a link in the chat for an exit poll, right? So just so we can improve these sessions for next time, we'd really appreciate if you guys spent a minute, 30 seconds to fill that out for us, just because we don't like to waste your time, right? So as long as you found this helpful, right, or if you have any suggestions to us, please feel free to let us know, right? I promise we won't get mad at you, right, or anything. We're just here to help you guys, right? So please feel free to fill that out. But other than that, I will go through a electric flux problem. And the one I chose was from the 2017 problem set, flux through base of pyramid, right, is what I chose to work with. All right, and the good thing about flux problems is they really can't get more difficult than this, right? We can change the shape, we can change kind of what the expression is that we give you, but we can't change how difficult it is, right? So just to cover that real quick, all right? But just to reiterate one more time, sorry, it is the flux through base of pyramid, right, and can be found on the practice exam problems from 2017. All right, so I'll give you guys a second to catch up there. All right, thank you very much for that comment in the chat. We appreciate it. That's all Nick for all the slides, so thank him for that. But it looks like I will go ahead and get started. So pull the problem in my other long camera tab, right? So when we look at this problem, right, we see this equilateral tetrahedron, right? This pyramid-looking shape, okay? And we've got a non-uniformly charged sphere sitting in the center of it, right? And we know the radius of that sphere and the volume charge density of it, right? Again, another row type deal, right? So I'm really not even going to bother drawing the picture just because I'm so bad at drawing shapes like this. But we're asked what the electric flux is, right, through the base, just the base of the pyramid, right? So that would mean the very bottom surface of it, okay? So kind of revisiting what I talked about at the very, very beginning of my spiel about Gauss's law, right, is that electric flux has two equations, right? In general, yes, I'm consenting to being recorded. Weird. Cool. Okay, sorry. Electric flux has two equations, right? It is the surface integral, right, of E dot dA, or, right, that charge enclosed over epsilon naught, right? I can use either one of those when it comes to any electric flux problem, right? So what I like to do most, or like to do first, I guess is what I should say, is just take an assessment of what I've got in the problem. All I know is that I've got some radius, right? I'll just write it out as some number, right? And then I've got a function for rho, right? In this case, I believe was, I think 3r, I believe, yes, 3r for me. That may change for you guys, but mine was 3r, for example, right? So we know that's non-uniform, right? Because it depends on r, right? So I don't know about you guys, but when I take a look at this information that is given to me, right, I'm immediately starting to think, you know, this left-hand side really isn't that useful to me, right? And the reason I did that is because it gives me a charge density over here. It gives me a rho, right? Rho, I know, is one of the pieces I can use to find this charge enclosed term, right? So immediately as I see that rho term, I'm like, okay, yeah, I really want to use the right-hand side because it's just going to be so much easier to do. Okay, so I'm gonna move forward with that, right? So Q enclosed, right? We remember integral of dq, right? And for a three-dimensional shape, integral of rho dv, right? So that should be these sorts of things should start to become a little bit more second nature to you about what the form of dq is that we're working with, right? But remember, I've got a three-dimensional object, so I need a three-dimensional expression for dq, right? Before I go any further, I'd like to say that the most confusing part about these types of questions is people are confused about what the dv should be. As in, I've got two shapes, right? I've got my pyramid, and then I've got my sphere of charge that's inside it, right? So little hint for you, we're never concerned about the shape of the thing that our charge is in, right? I don't care what the area of that shape is, okay? Never have, never will, right? I only care about the shape that has the charge in it, right? So in this case, it was literally just a sphere of charge, right? Sitting in the center of that pyramid, right? So that's all I've got. I've just got a sphere, right? So I know that the volume of a sphere, right, is 4/3 pi r cubed, right? So that makes dv equal to 4 pi r squared dr, right? And that just came from looking at the volume expression and then taking a derivative from there, right? Fairly straightforward, right? But it helps to remember what the volume expressions are so you can take derivatives and go from there, okay? So I'm going to plug in those two things, right? I've got the integral of rho, which was 3r for me, right? And then I've got dv, right, which was 4 pi r squared dr here, right? And so now your next question might be, okay, well, what are the bounds on this integral, right? So if I'm concerned about flux, right, I need all of the enclosed charge, right? I need all of it, right? So the problem gives me, way back up here in orange, the problem gave me the total radius of that sphere, right? The sphere that had charge. So seeing as I have nowhere else to go, right, no more information, I'm just going to integrate from 0 to r, right? Where r technically is a number, but I'm just going to keep it in variable form for now so you guys aren't confused as to where those numbers and everything went, right? So I'll just keep it as variable r for now, right? Again, pull out all my constants, right? So 12 pi out here, integrate 0 to r of r cubed dr, right? And then hopefully everybody can figure that out, that was 1/4 r to the 4th, right there, right? So to simplify, that would just be 3 pi r to the 4th, right? So that's my expression for Q enclosed, right? Again, so I've taken out most of the work for myself, right? I know the right-hand side of Gauss's law is just Q enclosed over epsilon naught, right? Way back over here, right? And I know epsilon naught's a constant, so I've really done all my work, right? I know I'm really very, very, very close to the answer, right? I just need to realize one more thing that the problem says. The problem asks for the flux through the base of the pyramid, right? Not through the whole thing, through the base, right? And a pyramid has 4 sides, right? So all I'm going to do is take my normal flux expression, right, which would have been Q enclosed over epsilon naught, right? And I'm going to divide it by 4, right? Because there's 4 surfaces that this could possibly go through, right? So I only want one of them. So I'm going to multiply by 1/4, right? And that would lead me to the final answer, right? It would just be that expression right there, right? And so there's, like I said, there's only so many ways we can switch this up on you guys, right? We can make it any shape we want, right? We can ask, oh, through these 3 sides that you can see, right? Or these 2 sides that you can see, something like that, right? But the general process never changes, right? It's just what can we confuse you guys on as far as the shape, right? Or the charge density, right? If it's uniform or non-uniform, right? But that's the reason why I did a non-uniform one, right? Because these are a little harder. The easier form of this problem is we'll literally just give you Q enclosed, right? They'll just give it to you straight up, right? And then you just have to find the flux from there. Yeah, so I gotta see a question real quick. Yeah, so can I explain why I divide by 4 specifically? Yeah, so again, I'm asked specifically in the problem, right? I apologize, I don't have the problem pulled up here, but it asks specifically for the flux through the base of the pyramid, right? Just the base, and the base meaning one of the 4 faces, right? So that's why. Do we need to know any odd volume formulas for the test? Also a very good question. The only 2 you guys need to know are the volume of a sphere and and the volume of a cylinder, right? Sphere would be 4/3 pi r cubed. Cylinder would be pi r squared L, right? That's all you would need, right? Nothing more, nothing fancier than that. All right, since a rectangular prism is uniform in shape of its sides, why do we divide by 6? Right, so Lisa, very good question. And I know the problem you're talking about. And fortunately for us, the problem asks for the 3 visible sides of the rectangular prism, right? So you would just multiply by 1/2, right? It splits out very, very evenly there. We wouldn't ask you for the flux through one side of the rectangular prism because, as you said it, right, there's 4 sides that look similar and then there's 2 squares, right? So we can't ask you for one surface of that, in other words, just because that area calculation would be too annoying, right? Could you explain again why we use the volume of a sphere for the charge enclosed of the pyramid? Yeah, so good question, Tristan. So again, remember, with my charge enclosed expression, I'm only concerned about where my charge is, right? I don't care what housing it's in necessarily. I just care about what object has my charge, right? So in this case, it's literally just a sphere, right? So integrating to find Q enclosed, right, it directly corresponds to what shape I have that has charge in it, right? If we would never ask you this because we don't expect you guys to know the differential volume of an equilateral tetrahedron or whatever it says, right? So that's also your other indication, right? You have no idea what that formula is, so you can't use it. Does that make sense, Tristan? I'll take that as a yes. Okay. I have one more question. So do the faces all have to be the same size, or can we always divide by the amount of faces? Yeah. So this kind of gets back to Elisa's question, right? If we're going to divide by the amount of faces, there has to be an equal number of them, right? So as in this example right here, every side of this pyramid was the same size, right? But in the example Lisa was talking about, that rectangular prism, it asks us for 2 rectangles and a square, right? So the three visible sides, which would be 3 out of the 6 sides total, right? So it'll be either one side because they're all the same, or it'll be a shape like a rectangular prism, right, where you can easily divide it in half. Does that make sense? Cool, awesome. All right. So that's all I wanted to go through as far as electric flux goes. Those problems are very straightforward. Go ahead, Nick.
Sorry, what were you going to say?
No, you're good. I was just going to say that's all I had for electric flux, right?
I'm really glad you went through that problem because you said that that's the only form of flux problem we'll see. But I think there might be one other one that we might see a form of. Do you mind if I go through that real quick?
No, not at all. I'm honestly kind of confused in which one you might be talking about. Go ahead.
Yeah. Let me share my screen. Because the problem that you just did, it was a flux problem, but to solve it, we sort of used Gauss's law with finding charge enclosed. But flux is sort of an independent topic. It appears in Gauss's law, but
yeah, I know the one you're talking about. Go ahead. Yeah.
There might be equations, or there might be problems that ask for flux that don't have anything to do with Gauss's law. So let me quickly run through one of those.
Yeah, I know what you're talking about. Yeah, good call.
Yeah, I'm glad we're doing this. And it's this problem right here. I don't think you have access to this, because it's from the final exam questions, but it says rectangular box. So suppose we've managed to set up an electric field that can be described by the function E, some I hat component, some J hat component, and some K hat component, and we're given the constants. Now let's take a look at a rectangular box in the Cartesian coordinate axes shown below with dimensions A, B, and C. So again, this is a flux problem because we're trying to find the magnitude of the flux passing through the shaded area, this side right here. But you can't really approach this with Gauss's law because there's no charges in this problem. There's an electric field, so we can just go back to the original definition of flux, but we're going to have to do it a little bit different. So if I pull up slides for that, that's right here. Yeah, rectangular box flux. So we're given this field. E is equal to W1 y squared I hat plus W2 z squared j hat plus W3 x squared k hat and a box. And we are trying to find the flux through this shaded side. Okay, so if we think back to the definition of flux, flux is defined by this integral. Flux is defined to be the integral of E dot dA. Notice this is a very similar thing that appears in Gauss's law. In Gauss's law, it's always a closed integral of E dot dA over some closed surface. but the surface doesn't have to be closed. In this particular case, we're considering the open surface that is this side right here. So if we have this E field given in I hat, J hat, and K hat form, we need to sort of break down what that integral comes out to. Because we have one component of the integral, we have the E field. But what do we do for dA? And thankfully, dAs for rectangular boxes aren't too terribly tricky. They're usually a little bit easier to figure out than spheres or cylinders, at least in my opinion. What I like to do here is I like to say, okay, the area in question, it's perpendicular to the y-axis. That is to say, it's sort of projected in the xz plane. So I can think of this area in question as being composed of, I guess, like little tiny partitions in the x direction, little dx's, and little dz's up here. And that gives me the differential area vector having a magnitude of dz dx. That's getting into Calc 3 territory where we would have to take a double integral because we have a dz and a dx. But there's another way to do this problem. And unfortunately, I can't write on the screen, but at least I don't think I can. Yeah, I probably can. But if my differential area vector I already claimed is dz dx, and it's in the j hat direction because area vectors are always normal to the surface that they describe. So if I'm describing this area vector right here, then the direction associated with that area vector is going to be in the j hat direction because that area is perpendicular to the y-axis. Again, area vectors are always normal to the surface that they define. So the area vector for this face right here is pointing in the y direction, so in the j hat direction. That's why I said my dA is equal to dz times dx j hat. Any questions on how I got my dA? Because I think that's a pretty important part. How Calc 3 will this intensive will this exam be? Hopefully not too intensive, because as we've seen with Tyler's examples in Gauss's law, yeah, we don't need to do area integrals to figure out Gauss's law. We can just go away with those by doing the simplifications. And what I'm about to show here is that this problem can be done without a double integral. What we have to do is we have to sort of look a little bit closer as to the form of the E field. So first of all, there's a dot product in this definition of flux. Flux asserts that I take the dot product of E and A. So if my E field is pointing in I hat, J hat, and K hat directions, and my area vector is pointing just in the J hat direction, again, because the area vector is perpendicular to the surface it describes, then let's see, the dot product between E and dA, the only component that matters is the J hat component. The I hat and K hat components go away. I don't even have to care about them because of the dot product. The dot product, if we want to get really mathematical, the dot product between I hat and J hat is 0, and the dot product between K hat and J hat is 0. But the dot product between J hat and J hat, since J hat is perpendicular to, or parallel to itself, is 1. So all I have to care about is the y direction. So if I look at the E field and I look at its J hat component, that's a z squared, which tells me that that electric field is non-uniform with respect to z. The electric field changes with respect to z, or at least the J hat component of the electric field changes with respect to z. And what that means for the area vector, shoot, I wish I could, let me pull out an online whiteboard or something because this really helps to write out. Whiteboard. Online whiteboard.
Hey, Nick, Zoom has a whiteboard you can pull up if you'd like.
Yep. I always forget about that.
Yeah, I do too. It sucks, but might as well, right?
Cancel. Shoot. Is it here? Shoot, where is that whiteboard? Do I have to be a host to see it?
I wonder. I mean, it's usually in the share screen option because that's where I have if I do it on my iPad. But I guess it may be different. I guess if you're on a computer, I didn't think about that. It should be under the share screen. You should get the option to share a whiteboard instead.
I am not seeing it. Let me find an online whiteboard. I think.
Yeah.
That's
Sorry. Go ahead. Go ahead.
No, he's fine. Okay. Online whiteboard. Here we go. Yeah, let's sort of draw this out, and I'll do as best as I can with the mouse. But what we have is a rectangular box, and I'm trying to find the flux through this side right here. Again, the y-axis is pointing along here, and then I have the x-axis here, and the z-axis pointing straight up. Sorry, that got a little bit cut off, but I have the z-axis right there. And I'm trying to find the flux through this side. And the electric field that I am given is, if I go back to long kappa, it's something I had. Again, I don't care about the I hat or K hat components. I do care about the J hat component, and that's, it looks like W2 Z squared J hat. W2 Z squared J hat. And that tells me that the electric field is non-uniform with respect to Z, which means that my differential area vector, this is the part that I really want to show, because it's, you don't need Calc 3 for what I'm about to show. That means that the differential area vector, it needs to contain a dz in it. Because this is the J hat component of the E field, and the J hat component of the E field depends on Z in some way, that means I need to integrate with respect to Z somehow. So I need to figure out some other way to partition my area other than dx. What I had before was dA is equal to dz times dx, which is true, because essentially what I'm doing there, if I erase, oh, that's a dumb eraser. I don't know. Shoot, okay. This whiteboard's stupid. But essentially what I'm doing with this partitioning scheme for saying dA is equal to, there we go. dA is equal to dz dx is I'm partitioning my differential area vertically like this and like that, such that these little vertical chunks all have height dz, and these little horizontal chunks have length dx, if you will. But the alternative method to define my area vector is to say that I don't want to partition my area like that. And if I instead erase all this garbage right here, there we go. That's easier. If I erase all this garbage right here, and again, I just look at this face, I know I have to have some sort of Z in my differential area. So instead, what I'm going to do is partition my area like so into these little long slivers. And what that means is that these long slivers, they still have height dz, because that's the infinitesimal length in the z direction, parallel to the z axis. But now their length is just whatever the length of this box is. And it looks like the length of that box is A. So alternatively, what I could say for my differential area is that it's just A, which is this length right here, A times dz. And awesome, because now I have a differential area that depends on Z, which is what I wanted, and it only has one d something in it, which means it's only going to be a single integral. So if I set up my integral for flux, flux is the integral of E dot dA. E dot dA. And then the E field, or the J component, J hat component of the E field is W2Z squared. W2Z squared. And then my differential area now, I can say is A, which is just a constant, times dz. That's it. That's all I need to do is to set up my integral. And then the bounds of integration, well, I'm integrating with respect to z. So the bounds of integration should be from the z coordinate where I start to the z coordinate where I end, which if I go back to the problem is from 0 to c, because that's the height of the box in the z direction. So from 0 to c. And now I think I can return back to my slides here. Yeah. So in what I did in my slides here is I just did it the double integral way, but it comes out to be the same answer. I pull out an a in either case. The w2 is also a constant, and I'm left with the integral from 0 to c of z squared dz, which is c cubed over 3. Did I miss anything in that problem, or does that all sort of make sense? Or assume here it is. All right, what did I say that doesn't make sense, or that needs more clarification?
No, Nick, I think you're good.
Cool, cool.
Sorry, I was trying to give you a thumbs up there. I don't know how weird that looked, but it was supposed to be a thumbs up. Cool. Well, guys, at this point, we're officially over the allotted time. Nick and I definitely don't mind staying, but just let you guys know there's no more like scheduled material after this necessarily. It's just open floor for questions. If you guys have anything about logistical questions about the exam, or like just want to go over a concept again, things like that, we're more than happy to do that. So feel free to unmute and say something, or to type it in the chat. It's all good. But yeah, so that's all the material we have planned, though. Thanks again for coming, and we hope you guys enjoyed it. Hope you guys found it useful. Of course, yes. Thank you. You're welcome, everybody. Thank you very much. Nick, we got one about diagonal equipotentials, and then flux through the cylinder. So why don't you do diagonal equipotentials, and then I'll flux through cylinder. That sound fair?
Yeah. Which one should we do first?
I have flux through cylinder somewhat pulled up, so I have no problems doing that first. Real quick. Yeah, the recording will be posted as soon as we're finished here. Zoom automatically sends that recording to whoever started the meeting in the first place, which should be Todd Ruskell, Dr. Ruskell, because he owns this Zoom room technically. So it should be posted sometime later tonight, but very least probably tomorrow morning, but we'll see. And then again, you will have access to the slides. Go ahead.
Yeah, I didn't send them out beforehand because it's hard to find typos unless you're actually walking through them. So I just got them corrected, and then we'll probably, to make things as concise as possible, we'll send them in the same email as the recording. So yeah, hopefully tonight at the very latest tomorrow morning.
Yeah. All right, cool. So let me share my screen real quick to talk about the flux through the cylinder. And so guys, I believe for those of you that are still around, it should be either 2017 or 2011. And I think about 3/4 of the way through, I think. It's literally just called flux through cylinder. Flux through cylinder. All right. So this problem is more like the first example I went through, right? Not the one that Nick just went through, but I'm very glad that he brought that up, definitely, because those problems are they're a little bit more. They're a little bit, I should say this, they're a little bit closer to calc-free stuff, as in you could use calc-free to solve those sorts of things. But that's pretty much what we mean by as intensive as it might get, right? Is you could use this to do it, but if not, that's totally fine. You don't have to. All right, so I don't have the picture pulled up, but I do remember what it looks like. All right, it's basically this cylindrical, whoops, I'm just gonna draw it, right? This cylinder, right? And then you've got an infinite sheet that basically bisects it about in the middle, right? Something like that. And the problem gives you the charge density of that infinite sheet, right? It gives it to you as some number, right? So you know it's uniform, right? Uniform, check, right? And then it gives you the area of one of these end caps of the cylinder, right? It'll say that it's some number, right? That's just my notation for some number, right? And then it asks, sorry, I guess it also gives you the length, the side length of the cylinder as well. And that's, again, some number. right? So it asks us what's basically just straight up, what's the flux through the cylinder, right? And you're left with these 3 pieces of information right here, right? So again, we kind of have to make a judgment call on what equation for flux we want to even use, right? So remember that it's both of those sides, right? E dot dA or Q enclosed over epsilon naught. Right. So again, either one of those sides I could use, right? It's really just up to me. Right. And this one tries to make it a little bit more confusing on you guys by giving you more of a choice as to where you want to go. Right. So it gives you area, sigma, and length, right? Again, this is another one of those cases where I would 100%, as soon as I see sigma and A, I am absolutely going for the right-hand side, right? I don't want to mess with the left-hand side if I can help it, right? Again, because I would have to go through finding the E field expression, which would be, like we know, right? It would be originating from some form of Coulomb's law, right? Or something along those lines, right? And we just don't have enough information immediately available to us to make that easy, right? So I'm just going to ignore it entirely, right? That just seems like way more work for myself than I want to do, right? So we're going to just solve for Q enclosed again, right? It seems like a pretty straightforward approach. So again, right, integral of dq. Right, so now you might scratch your head a little bit as to what dimension we're actually in. But the problem does give you a hint because it says that you have a 2-dimensional charge density sigma, right? So that immediately gives it away, right? But if that, let's say that wasn't given to you, right, and you were just given the picture, right, you would look at it and say, well, okay, I got this cylinder here, right, but I've also got this infinite sheet of charge, right? Remember that my dq expression is always concerned about what has my charge, right? Not necessarily what the object's in, right? What has my charge, right? In this case, it's this infinite sheet there, right? Not the cylinder, but this infinite sheet, okay? That's why I'm going to use sigma dA here, right, instead of rho dV, for example. Okay, so like I said, mental gymnastics, right? Do that first before you start writing things down, right? Establish a clear direction where you want to go before you actually go there, right? I see one question real quick. Could you explain the conceptual aspects of electric potential? Okay, yeah, sorry, we'll go through that when Nick's on this problem. Cool. All right, so back to this. All right, so integral of dq, which I know will be integral of sigma dA, right? And then this problem, the good thing about it is that sigma is given to you as a number. Right, that's just what that little pound sign there means, right? It's given to us as a number, meaning it's constant, right? It's uniform throughout my shape, right? So I can pull it out of the integral, right? Integral of dA, everybody said, is just A, right? So really, my charge enclosed is just sigma times A, right? And I'm given both of those numbers straight up, right? No funny business. I'm just given the numbers, right? So from here, it's fairly straightforward, right? I'm just going to take sigma times A, plug that in for charge enclosed, and divide it by epsilon naught, and that's it. Right? There's no fancy integrating we have to do this time, right? We don't have to divide by the amount of surfaces because we just want to know what the flux through the entire cylinder is, right? So it would just be whatever goes in on this side, right, is going to come out on the bottom anyway. So I don't need to divide by 2, right? It would just be sigma times A over epsilon naught, right? So if I were to summarize that, right? Sigma A over epsilon naught. And that's all there is to it. I believe it was Tristan that asked for this question. Does that make sense from a mathematical / conceptual perspective? Is that kind of answer your question? Cool. All right. Yeah. And sorry, it must have been not Tristan. Sorry about that. I apologize for getting the name wrong. That's my bad. But good. Glad it makes sense. And like I said, if you have any other questions, either you can unmute yourself and ask them in the chat if you'd like. But at this point, that's probably enough for electric flux. I will pass the torch again to Nick to talk about that equipotential problem and to address that good question in the chat by Catherine. So Nick, the floor is all yours again.
Awesome. Thank you.
Yeah, no problem.
Shoot. Let me share my screen. Here it is, and let me navigate to that problem. I think it was in 2011. Diagonal equipotentials, yeah, cool. And let me zoom in case it's hard to see. Cool. All right, so we're given this picture in the XY plane, and then we have these diagonal equipotential lines. Here's one that corresponds to some place where voltage is 0 volts, and then 100 volts, and then 200 volts. The picture above shows some equipotential lines. Each tick on the x and y axes corresponds to 1 meter. Use the picture to figure out the y component of the electric field in the region shown. Okay, so we're given potentials and we need to find E field. We have an equation for that. I guess I have to bring back the whiteboard that I just closed. Nope, not Desmos. History, here we go. So we have an equation for whenever we have the potential, such as what we have here, and we need to find the electric field. In this case, we need to find the electric field in the y direction, or the y component of the electric field. So that's just going to be the negative derivative of the voltage with respect to y. Cool. And now, if I remind myself of what the thing looks like, all right, so we have the y-axis going up there, and then the x-axis going across like that. And the equipotential lines, they sort of, whoops, wrong thing. Where'd it go? Here it is. The equipotential lines are sort of diagonal, and it starts 0 volts like that, and then 100 volts, then 200 volts, and so on. Okay, so we're being told to find the electric field, and we have the potential. What that means is we need to take the negative derivative. And we have the potential, but we have the potential. We sort of have to interpret what the potential is from this graphical representation that they gave us. We have these equipotential lines, but what's an actual function that I can take the derivative of to find the potential? Well, it's going to be a linear function because I can see that incrementally as I step up as I move incremental units in my y direction, the voltage changes by some amount. And what is that amount going to be? Well, let's see. We're told that each tick corresponds to 1 meter. And let's see, to go from 0 volts right here to 100 volts, that's 3 ticks. So it looks like for 1 tick, I gain 100 over 3 times y. And then, let's see, my y, if I start at 0, it looks like my voltage is that's negative 100, negative something, negative 133. Really, it doesn't matter too much what the voltage is or what the y-intercept is here, because again, we're trying to find the E field, so that means I only care about the derivative of the voltage. So I don't really care about this intercept here. What I'm really interested in is the fact that if I go a tick mark up, my voltage increases by 100 over 3. Let's test that equation. Or no, I guess we can just take the derivative or the negative derivative to find the electric field. So the electric field is just going to be negative 100 over 3. And let's see, did I do that right? So this is 0 volts if I look at my picture. This is 100 volts. And this is 200 volts. And again, I'm going to say the phrase that I like to say over and over again. Electric field lines point downhill with respect to potential. So my electric field looks something like that because it's pointing downhill with respect to potential. So the electric field should have a negative y component. So yeah, that makes sense. And let's enter it into long cap to make sure. 100 divided by 3 is 33. And electric field is going to be volts per meter. Cool. Did that process make sense for everyone? Cool. Hopefully that silence says yes. Again, I don't really have to worry about, or rather, I know that my electric potential function, my V function, is going to be linear because I have a linear increment of my voltage for every linear increment in Y. I don't really care about, I guess I only care about the slope of that linear function because I'm trying to take a derivative anyway. Cool. And now here's another question. In what direction will a proton move if we release it from rest at the point indicated? So the point indicated is here, and a proton has positive charge. I already drew the electric field lines that are pointing downhill with respect to voltage. And protons, by virtue of being positively charged, they always move in the direction of E field lines. So a proton released here is going to move down into the left. Cool. Any questions about that? If there's anything that I said that doesn't make sense, feel free to speak up, because when I'm drawing over there, I don't see the chat. But yeah, it looks like Tyler's doing a great job of getting the questions.
Cool. Well, that's 2 more questions. There's still 30 of you in here, which are fantastic. We had a record number tonight, Nick. We had 130, I think, is what we capped out at. So that's great.
Nice.
Anybody else that's left have any lingering questions about anything at all? See the proton orbiting charged sphere. Yes, we went over the rectangular prism one. We should have gone over that, right? So that'll be in the recording. Yeah, we haven't done the orbiting proton, right? Any other questions?
I had one in the chat, but I was just wondering, so if you had 2 positive charges, obviously they want to repel each other. So if you were to bring them together, there'd be an increase in potential energy. Is that correct?
Yep.
Mm-hmm.
Again,
Go ahead. Go ahead, Nick.
Sorry. Yeah, the equation for if I have 2 point charges and I want to find the potential energy between them, it's U is equal to K Q1 Q2 over R. Sort of analogous to how in Phys 1, the potential energy of two massive bodies is G M1 M2 over R. So that R in the denominator indicates that if my R is small, if I bring them close together, then the potential energy goes up.
Okay, thank you.
And I just now remembered before we started the other problem, there was the thing in the chat earlier about shoot, what was it? It had to do with potential. Oh yeah,
I think that. You think?
Yeah, like how potential conservative paths and stuff.
Oh yeah. Mm-hmm.
Yeah. Let me just run over that real quick. So if I share my screen one more time.
Great question, Catherine.
Yeah. And then I go here. Yeah. Okay. So the question was about conservative vector fields. The idea to remember here is that whenever we're doing statics, whenever charges are stationary and they're not moved, the electric field set up by those charges, so I guess I'll move here. This electric field is what's known as a conservative E field. And conservative just means that basically anything is path independent. So if I want to find the change in potential, let me go to my whiteboard actually. Oops, nope. Sorry, history whiteboard. So if I have, let's just do a single point charge, a positive charge like that, and it's creating E field lines that point outward. If it's a static charge, if the charge isn't moving, then that electric field is going to be conservative. And what that means is that everything is path independent. Oh, shoot. I did not want to do that. I wanted to change the color of my thing. There we go. So that means if I wanted to find, let's see, the change in voltage from going from here to here, for instance, it doesn't matter what path I take. All that matters is I look at the final and starting endpoints. This is sort of harking at the equation delta V is equal to the negative integral of E dot dl, which I didn't touch on too much because that's more of a topic 1F thing. But effectively, because I'm taking the integral of an E field over some differential length, this integral is what's path independent. I can take it over any path I want. And as long as my starting and ending points are the same, my potential is going to be the same. And one corollary, I don't know what the right term is, to this point is that if I'm looking at the change in V over a closed path, E dot dl, if that path is closed, meaning I start at one point and then I return to that point over any arbitrary path, the delta V has to be 0 because my starting and ending points are the same. I did not say that well at all. That probably made no sense. Unless it didn't.
No, I would say, Nick, that's pretty good. Yeah.
Okay.
That's
cool. Yeah, it's not a topic that's super duper important for this test, I don't think. Because again, the delta V equals the integral of, or negative integral of E dot dl. That's a topic 1F thing for the most part, but it's just good to know.
Yeah. Cool. Yeah, very, very good question, Catherine. That's a very, very good question. So it looks like I'll do the orbiting electron problem from 2017, and then it looks like we will probably call it because that's the last question it looks like that we have. So if you have any questions about anything, right, feel free to keep asking in the chat, or like I said, send us an email or come to Review Studio tomorrow, something like that. So we'll cover that. Whoops, not whiteboard. Sorry. Cover that question real quick, and then looks like we will head off for the night. So we were talking about let me just check and make sure I'm looking at the right one here. We're talking about the orbiting electron problem. Should be the third one from the 2017 exam, I believe. And it gives us a hypothetical situation, right, where you've got some charge. I can't remember if it gives it to you as a proton or not, but then you've got some electron, right, moving right in a circle around it, right, obviously orbiting this charge, right? You're given a couple of things. You're given actually, no, you're only given one thing, right? I believe you're given the radius at which it is orbiting this charge, right? Or the radius of the charge. Either way, you can basically assume it's on like basically orbiting pretty much the edge of that charge, right? Either way, the radius is going to be useful to us. So it gives it to us as some number, right? Like I said, long cap randomly generates everybody's numbers. So it's just going to be some number, right? And really, that's all we have to work with, right? We just want to know what the velocity of that electron would be. So something that's good to realize sooner or later in Phys 2 is that we use a lot of circular motion relations, right? And in particular, right, if I've got an electron moving in around orbiting something, right, moving in a circle, orbiting something, right, inherently I've got two forces that are at balance there, right? Hopefully you remember from Phys 1, I've got the centripetal force, right, being balanced with, in this case, my electric force, right, because I've got an electrically charged particle, right? So Fc equals Fe. Right, meaning that I've got m times ac, right, where acceleration centripetal is mv squared over r, right? Or I'll just write it as a little lowercase r. That's more like it. Right, so hopefully you guys remember that centripetal acceleration formula from Phys 1, right? And then from Phys 2, right, the electric force, this should be on your equation sheet, is just going to be Q times the electric field in the region that charge is experiencing, okay? So, and then that electric field, right, takes the form of Coulomb's law, right, which would be KQ over R squared. So I'm going to write that. Q times KQ over R squared here. Right, and so notice that I've got two Q's, right? In this case, they are the exact same, right, because I believe that the electron is orbiting a proton, something like that, right? So those two charges are going to be exactly the same, right? They've got the same magnitude of fundamental charge, right? So I can, for all intents and purposes, I can pretty much ignore, right, any signs from those, right? So really, I've got mv squared over r is equal to kq squared over r squared, right? And then I think you guys can pretty much see from here, we have all of this information, right, on our equation sheet, right? Mass of an electron is at the bottom, right? Charge of an electron at the bottom, okay? You guessed it, at the bottom of the equation sheet, right? So all of these things we have, right? We're only given the radius because that's all we need. So you can just set up your equation to solve for velocity to be the square root of, if I can do math correctly, so kq squared over mr, right? If I can do math correctly. right? So that's pretty much all there is to that problem, right? I'm sure there's different ways of doing it. I saw somebody in office hours the other day doing it with Gauss's law, right? Completely fair, right? You can do it that way if you want. I just think it's a little bit more roundabout, a little bit more confusing, but that's just me. But yeah, I forget who asked the question. I believe it was, yeah, Alex, right, cool. That makes sense, sounds good. All right. So at this point, like I said, I think we've answered every question that was voted on, at least to some degree, right? If you guys have anything else, feel free to drop it in the chat. Otherwise, looks like we will head off for the night. Yeah, of course, guys, it's our pleasure. We just hope you enjoyed it. Right, if you have feedback for any of us, Nick and I are both in the 10 a.m. studio. Feel free to yell at us to come over and you can tell us anything you'd like. Right, that's not a big deal. All right, we appreciate it. Thanks very much. Have a good night, guys.
Thank you, guys, and good questions, Catherine.
No worries, Chandler. Have a good night.
Thanks for coming, everyone.
Yeah, we appreciate it.
Definitely makes it worthwhile for us to do these.
Yeah, it's definitely sucks into an empty room.
It's not fun doing this for like, I think it was like 13 people last time we did for the final exam last semester.
Yeah, that was a little rough. But we got through it. All right, Nick, because this is still recording, I'm going to stop it and just end it for everybody. That way the recording gets sent to Todd. But obviously
Perfect.
we can text and talk about whatever. So sounds good.
Perfect.
All right, everybody have a great night. Thank you all for coming. We'll see you on Thursday for the exam.